Hi, in our second video about cosmology, we're going to discuss the ideas of Isaac Newton and how that has transformed our understanding of cosmology up to what we understand today, and give the best description we have of our universe as it stands right now. So, Isaac Newton. Sir Isaac Newton was a particularly important scientist and mathematician in the history of physics. And prior to his work, most of the descriptions that we had of the universe were based off of what Galileo had told us. Now, Galileo was incredibly smart, and he made lots of really great observations and descriptions of the universe, but a lot of his work was missing something really important, and that thing was why. Why did the observations he made happen? Why did the universe behave the way it did? Now, Newton tried to give us this answer, and in fact has given us a really great description of why the universe behaves the way it does. In 1687, he wrote his book, The Philosophiae Naturalis Principia Mathematica, or The Mathematical Principles of Natural Philosophy, as it would be in English. There's a bit of a cover there. And he gave us descriptions of why things move, or more particularly, why things change the way they move, change their motion. And fundamentally, this is because they are either pushed or pulled by something. Now, this is probably pretty obvious to us today, but it's really important to acknowledge that Newton was basically the first person to actually really write about this, and to actually identify the fact that objects won't change their motion unless they are pushed or pulled, made to do so. And the thing that makes these pushes and pulls, makes objects change their motion, this is what we call a force. Forces are the things that push objects or pull objects and make them change their motion. So there's a number of different forces. A lot of them you'd be very, very familiar with. Contact forces. So you can literally pick something up. You can push it or you can pull it. Do it with your hands. That is the application of a force. Friction is another force. When two things are touching each other or moving past each other, they will get warm. They slow each other down. The two objects have contact, rub on each other, and they actually slow each other down. This is friction. Magnets, magnetic forces, electric forces, there's a whole range of other ones. But Newton's forces describe the changes of the motion to virtually any object on Earth basically perfectly. And they describe what's going to happen in space, describe the way things move and change. So anytime that we're talking about forces, we actually measure the strength of that force, and we measure it in a unit called newtons to honour Sir Isaac. So a force of 5 newtons is less than a force of 10 newtons, for example. 10 newtons is a harder push on an object. Now, of all the forces that there are, the one that has the biggest influence in space is gravity. Gravity is able to act over the vast distances in space and make some significant influence over the universe. So gravitation, Newton came up with a law. He described the law of gravitation that states the following: any two objects will attract each other proportional to the product of their masses and inversely proportional to the square of the distances between them. So we can simplify that a little and understand that any object actually produces gravity. Any object that has mass has gravity. So you and I, your computers, your tables, anything, they have mass and therefore they have gravity. But the bigger the object is, the more gravity it has, the more gravity it creates. So something like the planet Earth, which is much, much heavier than you or I, obviously produces a lot more gravitational force than a small object would, like you or I. The other part of this law is the distance between the objects makes a difference to how much force they experience. So if you are close to something, you experience more gravitational force. Further away, the less force that you're going to feel. So Newton's law of universal gravitation gave a really good description of the way that any two objects will interact and therefore what's going to happen. So it really gave us a new way to describe the universe. It allowed us to explain why the moon orbits the Earth, why the planets orbit the sun, why stars look like they are orbiting each other, why they move around. And you can actually use it to determine the gravitational force between yourself and any other object in the universe, as long as you know how big that object is and how far away it is. So here is the equation. We're going to use this later in the course, so I want to show it to you now, but we're not going to worry about it in great detail at the moment. So this is the equation here. Fg, force due to gravity, is equal to g, which is known as the universal gravitational constant. You can see the number on the screen in front below you. M1 and M2 are the two masses of the objects, so for example yourself and the planet, and d is the distance between those two objects. So when you know those values, you know the distances or the masses of those planets or other objects, you just substitute those numbers in instead of those symbols, the letters, and that will give you the strength of the gravitational force between those objects. So that was Newton's work. Einstein is the next person who contributed significantly to our understanding of the universe. So Albert Einstein, or a better picture perhaps, he added and changed Newton's laws of gravitation. Newton's descriptions were the best we had until 1905. At this point in time, there was a lot of evidence that suggested that there was some problems with Newton's model. It worked really well here on Earth, basically perfectly here on Earth. But up in space, there seemed to be things that weren't quite right. The observations didn't quite match Newton's theory perfectly. And so in 1905, Einstein started to publish the work that would come to explain this later. He produced a series of papers that explained some strange observations about the universe, and this became what was known as special relativity. 10 years later, he actually published another theory, or a series of papers that created another theory, which was actually called general relativity. So we have special relativity and general relativity. Now, these two theories actually describe the universe perfectly to the best ability that we have. People are constantly trying to disprove these ideas or trying to find evidence that relativity in either of its forms is wrong. But as at yet, all of the predictions of the theories work and they all match up perfectly with the evidence that we've been able to collect about the universe so far. So these are really, really complicated ideas, but I'm going to try and simplify them as best as I can for you here. First of all, special relativity. This works on the idea that the fastest thing in the universe is the speed of light, and nothing can actually get faster than the speed of light. So if any object starts to travel faster and faster and gets close to this speed of light, the universe actually changes. It stretches, it squashes, time and mass all alter so that the object can't actually get any faster. General relativity. This is another strange idea, but instead of force being something literally pushing or pulling, the force of gravity is actually produced by the mass of the objects bending space around it, creating a dent in space-time where objects in orbit or objects that are falling are actually basically rolling downhill into one another. So these are really big ideas, and we don't You don't really need to know much about them more than that. But if you're interested, you can come and talk to me in class, or send me an email or something like that. So after these two big ideas, what else do we know? So 1922, Alexander Friedman did some calculations using Einstein's work and suggested that the universe might actually be getting bigger. It's not just sitting still, it's not staying how it was, it's actually expanding. 1929, Edwin Hubble made some extra observations that actually supported this idea. He figured out that galaxies actually were moving away from us, moving away from each other too. And the further away they were, the faster they were moving. Strangely, Hubble himself didn't actually like this idea. He thought he was wrong. He thought the observations must have been wrong. But turns out he did some excellent science, and his observations were correct. 1927, around the same time, a man named Georges Lemaitre, who was actually a priest in Belgium, he described an idea that extended some of this idea, this concept. What he thought was this: if the universe is getting bigger now, and it's going to keep getting bigger in the future, if we went backwards in the past, it must have got smaller. And if you go far enough back in the past, everything would have been so close together that it actually has to have been in the same place. So this was the very beginnings of the idea that now we know as the Big Bang. So the Big Bang, the theory of the Big Bang. More this. The idea is this. The actual detail is very complex, but the idea is quite simple. The entire universe, everything in the universe used to be compressed into a space smaller than a tennis ball. And that's possibly infinitely small. At some point in time, there was an explosion, a violent, hot explosion that caused everything in the universe to expand outwards and keep going. Because all of the universe was in this one place, everything that exploded was the universe, which means the Big Bang happened everywhere. The whole universe expands from everywhere, which means everywhere is the center of the universe. Including you. You are the center of the universe. So this is a really tricky idea. The beginnings of the universe, everything that is the universe was compressed into this single space. All of the stuff, that's maybe okay. But all of the space in between the stuff was compressed into this. And all of the time of the universe was compressed into this single space. So this is a very tricky idea to try and get your head around. There wasn't anything outside of this ball. It wasn't a little object floating around in empty space. This was space. There wasn't anything before this object because time didn't exist before this object. So it's a really tricky idea to get your head around. So if you don't understand that, if that doesn't make sense to you, that's absolutely fine. It doesn't make sense to most people. It doesn't really make sense to me, but it's what the data tells us. The last thing we'll finish on quickly is some of the evidence that tells us this is correct. So Hubble made his observations that said the galaxies were moving away from each other. The other big thing we have is the cosmic microwave background. What this is actually a leftover heat from the Big Bang. These two gentlemen, Penzias and Wilson, discovered this background radiation was coming from everywhere. And they actually mapped it, and here it is. This is a map of the entire universe and the radiation. This is the leftover heat from the Big Bang. Alright, in the next video we will have a look at what comes next. What are some of the other big questions for cosmology? Alright, thanks everybody.